Okay, I think we better get started. Today's lecture is going to be focused on Gaussian distributions and a technique called a QQ plot. We're going to transition the next lecture after this. We're going to talk about the central limit theorem and confidence intervals, and that's going to set us up to then talk about t-tests, which I think many of you have probably used. But we're going to get into the theory of how a t-test actually works and exactly how it's computing a p-value. The lecture after that, we're actually going to talk about inference and p-values. That'll probably take us way into October, I guess. And then from there, we're going to get into probably 5 to 6 lectures on linear regression and generalized linear models, which will probably take us through the end of the semester. So just to set things up, a few weeks ago, we talked about a discrete random variable, a Poisson random variable and Poisson distributions. And just by contrast, remember that discrete random variables only take on integer values, right? So this is used to model things like, the number of light bulbs that burn out in the warehouse, or the number of DNA sequencing reads aligned to a particular position in the genome when you have an average depth that you've shot for, or the number of green M&Ms in a bag. By contrast, what we're going to focus on today is the Gaussian distribution, which is an example of a continuous distribution. So Gaussian distributions come from continuous random variables. Things like, we talk about height as I'm 6 foot 1 inch, but I'm actually, the precision of that estimate is much, much larger. You can actually measure my height to infinite precision. And that's the same for everyone. So height is actually a continuous random variable. Distance between stars is your exact age down to the billionth of a second. And I think the really important thing to always recognize with continuous random variables is there are an infinite number of possible values when you get to when you're talking about unlimited precision in the estimate. Okay, so the Gaussian distribution or Gaussian random variables come from this guy named Johann Gauss. Probably all of you have heard of him, at least in one way or another before. He was an absolutely prolific mathematician. He was a child prodigy. My favorite story about him is apparently, who knows how much of this is actually true, but the way the story is told is that in his math class when he was 7, the teacher told all the students to compute the sum of the numbers 1 through 100. And all the other kids in the class started writing down 1, then 2, then 3. And on the time they had to write out all 100 numbers, Gauss raised his hand and said it's 5,050. And the teacher just sort of flabbergasted, how did you know that? And he recognized that there are 50 pairs. 1 and 100 add up to 101. 2 and 99 add up to 101. 3 and 98 add up to 101. There are 50 such pairs, so you multiply 50 times 101 and you get 50/50. And that sort of shocked the teacher, and from there on he was continuously surprising professors and became sort of a prodigious mathematician at a really, really early age. If you're into this, there's a really fantastic podcast about Gauss on this BBC podcast series called In Our Time. Check it out. Okay, so I think all of us know about the Gaussian distribution, or the normal distribution as it's also known. This is the famous bell curve. Here's an example on the right of 4 different Gaussian distributions. And if you recall the other week when we talked about Poisson distributions, there's one parameter to the Poisson distribution, right? Remember lambda? That is the mean. And that lambda for the Poisson distribution governs the variance in that distribution. As the mean increases in a Poisson distribution, so does the variance. This is a more sophisticated distribution. There's 2 parameters. We can control the mean, so where the central value is. This green one and the blue one have different means. And we can also control the variance, or the standard deviation, the spread of the distribution. Okay, so the red, orange, and blue distributions all have the same mean, 0, but they have very different standard deviations so that we can spread that distribution farther apart. They have fatter tails. Okay? And we can compute, we'll come back to this, but there's a fairly straightforward formula for computing. If we know the mean, or we have a good estimate of the mean and the standard deviation, we can compute the probability of any particular value x. On the left-hand side, the frequency of x given a mean, given a standard deviation, can be computed directly. And so oftentimes, and we'll get to this later in the lecture, if we believe that the data that we've collected follow a Gaussian distribution, if we can get a pretty good estimate of the mean and the standard deviation of our observed data, we can use that mean and standard deviation to do some pretty simple math to figure out probabilities of any particular value that we might see in the future, so forecasting. Okay, so Gaussian distributions or Gaussian random variables have this beautiful symmetric shape because the sources of the randomness that generates that variance are the result of contributions of many, many small random effects. So there's a famous little machine that Francis Galton invented called the bean machine. Has anyone heard of the bean machine? Seen this? Okay, great. Well, maybe one or two. It's also called the quincux, which I have no idea why it's called that. I tried to figure it out. If you've ever played pachinko, it's very much like pachinko. So Galton is famous for a couple of things, some good things, some really bad things. He's famous in statistics for essentially quantifying variance through this metric called standard deviation, which we've already talked about. And he also had pulled this famous trick at a fair, I guess, in England, where there was a prize if you could guess the weight of an ox after it was slaughtered and dressed, which is like why anyone would want to do that, I'm not sure. But apparently 800 people made a guess, and Galton somehow got access to all the guesses, sorted them in ascending order, and picked the middle value as sort of the representative or the median value. He hadn't sort of published on what a median was yet, but he had an intuition about it. And it turned out that that median value was within like 0.5% of the actual weight. And unfortunately, he was also an early proponent of eugenics, which we're not going to get into today, but that comes into some of the reasons why he was interested in human height and the heritability of height. Okay, so back to this bean machine or quincux, or it's also called the Galton board. The idea is you drop beads or pellets or BBs, whatever, at the top of this board, and the board let's see, I can use my mouse here. A bead falls through this little hole and hits these pegs and will go left or right with equal probability, 50-50 chance that it goes left or right. Okay, and so the idea is if you drop beads down this board, the beads collect in these piles, or these slots down the bottom, in what looks like very much like a Gaussian distribution. And I think this is a really nice illustration of the series or the combination of many, many small effects. These effects are each of these layers of pegs. They contribute a small amount to where the bead ends up, but taken together, all those things lead to most of the beads being kind of in the center, but rarely they go out to the right tail or to the left tail. Okay? So an analogy in human traits would be height. We know that this is polygenic. Our height is the combination of lots of contributions from the genes of our parents, but also things like environment, access to food, nutrition, all these things. Okay, So here's a simulation that I wrote to show you what the bean machine will do. You can copy and paste that code into R if you want, and it'll make this cool little plot of all these beads running down this board, and it'll build up this distribution over time. You can change the parameters. This only does simulates 200 balls falling down it, but you can, if you're bored, you can simulate 2 million and watch that for a couple hours if you want. Okay, but that's the basic idea. So that leads to this bell-shaped curve, or this normal Gaussian distribution. So we can use ggplot to draw what's called the standard normal distribution. And that's a term that I think I didn't really fully understand what people were talking about until maybe 5 or 6 years ago. But standard normal distribution is just the mean is 0 and the standard deviation is 1. And so this Gaussian distribution is centered at 0. You can see I've given it this function dnorm. Density, this is a density distribution from the normal distribution. I've given it mean 0, standard deviation 1. And this x, I've simulated a 100 values between -4 and 4. Okay? So it's taken that range, -4 to 4. We've seen this before. We're just simulating data, and it fills in 100 values that are uniformly spaced between -4 and 4. And then this dnorm function is calculating the probability of seeing a value between -4 and 4, all those 100 values, given a Gaussian distribution with a mean of 0 and a standard deviation of 1. And we're just plotting it, okay? So we can use R and a little bit of simulation. We can generate simulated data to make nice looking bell curves. Okay, but there's some important properties of the Gaussian distribution. And I think many of us are familiar with these. If you take the mean and go out 1 standard deviation above the mean and 1 standard deviation below the mean, the area under that curve represents 68.3% of the data. So in a normal distribution, if your data truly are normally distributed, within 1 standard deviation up and down the mean, you have over 2/3 of the data are represented there. When you move out to 2 standard deviations up, below, and above the mean, we get up just above 95% of the data. And 3 standard deviations is nearly 100% of the data, 99.7% of the data. So knowing what, if you have a Gaussian distribution with a predictable mean and a predictable standard deviation, you can use these facts to say how likely it is or unlikely it is to see a value that's 3.3 standard deviations above the mean, 4.2 standard deviations below. And essentially, you can directly compute a p-value, the probability that that value actually is below, that far out from the mean. And those distances from the mean, or those standard deviations, are also called z-scores. So z-scores are really convenient because it standardizes distance from the mean without caring at all what the mean is. So it allows us to abstract what the actual shape of the distribution is, but just talking about distance from the mean. And if we know that distance, we can directly compute the probability of being that far away from the mean. Does that make sense? So z-scores is really just, I don't really care what the parameters of the Gaussian distribution are, but you can use any z-score to, if you know the z-score, you can compute the probability. Okay? And we're going to come back to how z-scores are useful in QQ plots in a little bit. So if we had data about births, I'll say over the last decade, and we knew something about the mean weight of a newborn at birth and the standard deviation, we could use that information to compute a Gaussian distribution from those parameters and ask questions like, what's the probability of seeing a newborn with a particular weight? So what is the probability, what's the absolute probability of a baby being exactly 7 pounds at birth? Anyone have a guess? It's kind of a trick question, and the answer is right there. But it's a trick question because it's actually 0. Because the absolute probability of any particular number is 0, because there's an infinite number of possible values given infinite precision. But we know that you can actually compute estimates of the exact probability of a birth being, 3,700 or 175.15 grams. And that gets back to calculus. You're basically computing the integral over a very, very small range in that distribution and using that as an estimate of the probability. It's essentially a relative probability. You can't compute the exact point value, but you can compute the area under a curve for that value plus a little tiny epsilon. Okay, so it's 0. So this is the way it works. This is basically plugging in directly into this function I talked about. So I know I looked up at this website. There's a paper from a few years ago that says that the mean birth weight for newborns with parents between the age of 30 and 40, I think it was, is 3,586 grams, and the standard deviation is 460 grams. That makes sense. It's about like 7-ish pounds, 7+ pounds. Okay, so we can use that mean and standard deviation along with this D for density from the normal distribution to calculate the exact value of all weight, exact probability of all weights between 2,000 and 6,000 grams. I just chose those numbers arbitrarily. You could go all the way out to 0 grams, which I think is impossible, to 100,000 grams, right? And essentially what it's doing is computing, it's returning the probability. Here's the weight that I'm concerned with. Basically go vertically up into the distribution and find the y value at which the curve intersects that x value. And the probability, the relative probability that's returned is, again, that value plus a little tiny epsilon. And if you go back to calculus, you're computing an integral over that very, very small distance. Okay? All right. So we can compute the relative likelihood of all these different weights given a mean and a standard deviation. But this sets up sort of, I think, an important concept in probability distributions, which is the difference between a probability density function, a PDF, different kind of PDF here, versus a cumulative density function. Okay, so let's walk through this. So a probability density function is computing the value, the relative probability for any particular value, whereas the cumulative distribution function is computing the probability that a value is, all values are less than some particular value. So let's walk through an example. Let's say I compute, I'm looking up the probability at 3,000, the probability of a newborn being born at 3,000 grams. We know that the probability of that is something between 0.00025 and 0.0050. The associated value in the cumulative distribution function is actually this area right here that's to the left of that value. So the probability, the cumulative distribution function, is the probability of a newborn being born with a weight less than 3,000 grams is something like, I don't know, 0.1, something like that. Okay? And you can see that this cumulative distribution function is sigmoidal in shape. It's increasing and then it tapers off because when we get way out here, every value in the probability distribution density function up top is less than 6,000. So essentially, once we get up to weight of 6,000, essentially all values are going to be less than that. So let's march along. Let's say we're looking at 5,000. I'm sorry, 3,586, which is the mean. Well, we know that that's the mean, so it should be that 50% of the values are less than that mean. Okay, because this distribution is symmetric, the mean and the median are identical. Okay. And if we go all the way out to 5,000, we can see that the probability, the cumulative density function is saying that the probability of any value, birth weight, being less than 5,000 grams is nearly 1. 99.89% of births are expected to be under 5,000 grams. Does that make sense? So there's this tight relationship between, well, a direct relationship between the probability density function and the cumulative density function. And the cumulative density function is really useful for answering questions like this, which we just walked through. What's the probability of a birth weight being greater than or equal to 4,000 grams? Well, that's literally just using, we've switched now from D norm to using this P norm, which reflects all the R distributions, all the R functions that start with P, followed by norm, or P chi-squared, or PT. It's giving you values from this cumulative distribution function, whereas all the functions that start with D are coming from the probability density function. Okay? So I'm saying, what is the probability, I'm asking, what is the probability of birth weight being greater than or equal to 4,000 grams? And we can just plug that right in. But we have to do 1 minus, because this p-norm distribution is always computing the probability of it being less than whatever value we put in. So we can use the complement rule that we talked about a few weeks ago and just do 1 minus that, because the total probability has to add up to 1. So if we compute the probability of it being less than 4,000, we get that probability, and we just do 1 minus that probability, and it tells us the probability of that value being greater than. For those of you that are familiar with R, you can also just change this lower tail to be false. And lower tail, when lower tail is true, it's going below. If you flip it and say lower tail false, it's going above. Okay, so you can skip it. This is the same thing. So we can just say P norm, lower tail equal false. It's doing the exact same thing. Okay, we can also say what's the probability of a particular birth weight being in a range of values. So in this case, we have to compute the probability, first compute the probability of birth weight being 4,000 grams or less. That comes from using this p-norm function again. And we find that that is 0.815. Then we compute the probability of a birth weight being 3,000 grams or less. Same function, just plug in a different value, we get 0.1. And essentially, to compute the probability of being between these two ranges, we subtract the larger probability from the smaller to compute the area under this cumulative density function between those two values. And that tells us there's about a 71% chance that a given birth will be between 3,000 and 4,000 grams. Does that make sense? Okay. So, long story short, the reason we went through all this in somewhat gory detail is that if you know the mean and the standard deviation of your data and you think it's normally distributed, we'll talk about how to convince yourself of that in a second, you have access to all these really, really convenient functions to just directly compute the probability of all these different events. Okay? So we're going to get into thinking about or asking whether or not the data that we've collected are indeed normally distributed. And the way we're going to do that, we're actually going to go back to the data that Galton collected in his inquiry of the heredity of height. You may be familiar with that this data set. It's actually collecting heights of parents and their offspring. We're just going to focus on the heights of parents today. But the collection of both parental and offspring heights led to the formalization of this concept called a regression to the mean. And we're going to table that until we talk about regression in maybe a month or so. But this is an excerpt of the table that Galton put together looking at the heredity of height. It's barely legible, but mainly just there to jog your memory. What's nice is in R, we can actually get this data directly. Someone's gone through that paper and read that scanned PDF and like actually written out all the values that were collected to really high precision, which is super nice because I would never want to do that. So the data come from this library called Using R. And this Using R library has a bunch of really cool built-in data sets that allow you to just poke around and try different things with R. And one of them is this Galton data set. There are two data sets in the Using R package. One is called Galton. The other one is called father.son. We're using the father.son data set because it has these height values to really high precision. The Galton data set, I think, just has it in inches with no sub-inch precision. Okay, so I'm not going to run this code. I'm just going to tell you that it works. We can load up this data set called father.son. We can take a peek at it. We can see there's a vector called father heights, and then there's son heights. And these, I would guess, it looks like are in inches. And we can compute directly using tricks that we already know about. We can compute the mean of the father's height, which seems to be about, what is that, 5'7" and almost 3/4. And remember, this is collected in Victorian England, so I think the heights are a little bit shorter than they would be now. And the standard deviation is about 2.7 inches. Okay. So when you plot a histogram, first thing you do when you're exploring your data usually is plot a scatter plot or a histogram, just to get a sense of the range of values. If it's a scatter plot, if you're looking at two variables, you want to look at the correlation between the two. Here we just have one value that we're interested in, father's height. So I just made a simple histogram using ggplot. And you know, it's not a perfect bell curve, but it looks roughly like the distributions that we saw before. And there's values that are less than would be expected by a Gaussian distribution. There are values that are higher, more frequent than would be expected. And that gets at this concept of randomness. There were only, I don't know how many, if someone's loaded it up, you can tell me how many observations there are in there. It's probably hundreds at most. So some of this fluctuation about what might be expected for a Gaussian distribution are just sampling error. Okay? But it's not for sure that this is a Gaussian distribution. There are other distributions, continuous distributions, that look a lot like a Gaussian distribution. Does anyone have a sense of one? Yeah, the student's t distribution is one. The chi-squared distribution. They all are similar in shape to the Gaussian distribution. So if we imagine we collected this data and we wanted to ask whether or not our data are well modeled by a normal distribution, we would have to go through some machinations to actually prove to ourselves that it really is best modeled by a Gaussian distribution as opposed to a t distribution, which we'll talk about in a few weeks. So the way we do that is one very effective way of doing that is with what's called a quantile plot or a QQ plot. Has anyone ever used a QQ plot before? Yeah, see a couple nods. Is anyone familiar with how it works? Okay, we're going to get into the gory details of how it works and why it works. I want to introduce QQ plots before we move on to other topics like central limit theorem, because actually one of the hardest challenges in working with biological data is trying to figure out what is the theoretical distribution that best models my data. Because once you have that information, once you've made that decision, you're really empowered to do lots of pretty cool stuff, like using these built-in functions in R to directly compute probabilities. but you're not liberated to do that until you actually know what the underlying distribution most likely is. Okay, so the Q and the Q stand for quantile, and the plots generally look like this. You have so-called theoretical quantiles on the x-axis, that's the independent variable, and on the y-axis you have the quantiles from your observed data, your sample quantiles. We're going to talk about what that is, okay? But generally the plots look like this. This would be a so-called good QQ plot. The points line up on this y equal x diagonal. We'll talk about why that would be a good QQ plot. Okay, so first of all, we have to think about and define what a quantile is. Quantiles are taking a distribution or a collection of values and breaking them up into ranges that have the exact same number of values. Okay, so deciles, each decile, for instance, a decile is a quantile, and each decile has 10% of the data. Okay, so you're sorting the data from ascending to, or descending to an ascending order, smallest to largest, sorry. And if there were 100 values, each decile would have 10 values in it. The first decile would have the 10 smallest, the last decile would have the 10 largest values, okay? You can break them up into quartiles, which would be, there are 4 ranges, and each range has 25%. There's quintiles, 5 groups. I always forget this one, vigentile, which is 20 groups. But is there a question? Okay. So percentiles are 1%, right? So there's 100 percentiles. Each of those are all instances of quantiles. Okay, so the purpose of a QQ plot is to ask how similar is the distribution of quantiles in my observed data to theoretical quantiles from a distribution that I'm interested in comparing to, okay? And as we'll see in a second, when your observed data, the quantiles from your observed data are well aligned with the theoretical quantiles from, say, a normal distribution or a t distribution, things line up perfectly on this y equal x diagonal. Okay, so why would we care about this? I've mentioned it once or twice, but it's really the fact that knowing the underlying distribution really liberates us to exploit things like z-scores and to be able to directly compute p-values for, I know what the observed distribution is. What's the probability of seeing this really interesting outlier that I've just seen? Is it expected, given the theoretical distribution that I've proven to myself that my data follow, or is it unexpected? And usually we're kind of looking for unexpected things, right? But we have to convince ourselves that we're not wrong first. Okay, so let's take, created some toy data here. These are, I don't know what they are. They're just numbers. We could pretend they're anything. Let's say they're, heights in feet. I don't know. It doesn't matter. But we've got 9 observed values. I'm going to toggle now between R and my slides. So I'm going to load up this data set. Oops. Okay. I can use the sort function to sort, not surprisingly, these values from smallest to largest. Okay? All right. So if I were to break these up into deciles, there's 9 values. My first decile would be from 0 to 3.77. My second decile would be, I can't read it, from 3.77 to 4.25. And then third, 4.25 to 4.5, et cetera, right? Okay, those would be my observed deciles or quantiles. Okay. Now, when we make a QQ plot, the second step is to essentially draw in our heads a standard normal curve. And remember, the standard normal is mean 0, standard deviation 1. Okay? And if I've got 9 observed values, that means I'm going to use deciles. You add one more range to the number of values that you have. If you had 10 values, it'd be 11 deciles, whatever that is. We'd have 11 different ranges. Then what we do behind the scenes is we break up this standard normal curve into the same number of ranges, such that each range has the same area under curve. Okay? So we break up this standard normal into, say, 10 different ranges. And what's beautiful about the Gaussian distribution is that when we have those ranges, okay, range 1 goes from z negative 3 to z whatever that would be, I don't know, maybe negative 1 point something, we can directly compute what the area under curve is for that part, okay? And so we basically just know the ranges of the z-scores, the pair of z-scores that define each range in the standard normal. And all we're doing is plotting the values from our observed deciles against the theoretical values from the Gaussian deciles. And if our observed data come from a Gaussian distribution, those things will be perfectly lined up. It doesn't matter what our actual values are because we're abstracting this out to z-scores. If it doesn't lie on the diagonal line, then we can be pretty confident that our data are not well characterized by a Gaussian distribution. So let's make that a little less opaque. But essentially, hopefully you're all with me where we're just taking the standard normal and we're breaking it up into 10 values. If I had 100 observed data points, we'd break this up into percentiles. If I had 1,000, this distribution will be chopped up by R into 1,000 discrete intervals, and we just have to know the z-scores that are the beginning and end of each of those different intervals on the standard normal. Okay? I walked through all of this.
I got questions.
Yeah.
When you're saying that the z-score, meaning that your line of demarcation from the means, not the average within the
Z-scores from the standard normal, not from your data.
Yeah, but yeah, what I'm trying to say is that I guess you just pulled it up right there. I guess represented a red line rather than whether the cutoff line is.
Yes. So the first range of values would be from, say, -3 to negative 1.28, and the second range would be from negative 1.28 to whatever that is.
And the C value you will put in there would be that cutoff line from that point on.
Yes, those values. So if I'm trying to create deciles, for instance, what's going to happen behind the scenes? This will happen every time if you're ever doing a QQ plot with 9 values. It knows it has to break up the standard normal into 10 ranges, and those will literally be, every time will be the z-score values associated with that. Because it's directly computable either by using that p-norm function, or there's tables. I mean, this is actually just hard-coded and probably just hard-coded into R. I actually don't know. But before R existed, if you were doing this type of work in 1961, you would be looking up at a Z table and just figuring out exactly what the value was. Okay. So, for instance, let me try and draw this. If I'm trying to figure out what 10% of the if I'm trying to compute deciles, each interval has to represent 10% of the data. So the first thing I want to do is find the z-score whose area under curve to the left of it is 10%. So basically I'm looking at between -1, a z-score of -1.2 gives me an area under curve of 0.1151. And if I step up to -1.3 z-score, it's an area under curve of 0.0968. So the z-score associated with 10% of the data is somewhere between z equal -1.2 and z equal -1.3. And it turns out that the exact z-score that comprises 10% of the data in a standard normal is a -1.28. Does that make sense? So when we go to look at the QQ plot, the first point on the theoretical quantiles that's associated with our first observed value will be negative 1.28. Okay? I hope I'm right about that. Well, the second one, sorry. So what we're now we're plotting, I'm doing sort of a poor man's QQ plot. We've got our observed data, and then we get our z values that I computed directly from that table. And what we're plotting is the theoretical quantiles. These are z-scores associated with those quantiles. And in this case, we know they're deciles versus the observed quantiles, our actual data. The cut points in our actual data that define deciles. And what you can see is it's not perfect. I've drawn this, perfect y equal x line, but gosh, it's pretty close. Most of the points are right around that diagonal line.
Oh, so QQ plot knows how to scale it, your theoretical versus your data, where your data actually ranges a little different from the z.
Yeah, so thank you for asking that. That's one of the beauties of the Q plot. It doesn't matter what the range of your values are. What matters is how many values there are. So if there's 10 values, if there's 9 values, it's going to know to break it up into deciles. If you've got 1 million values, it's going to know to break up that standard normal into 1 million different slices. And the range, the y range, will be defined by the range of your values. And the x range will just go farther and farther out into the wee tails of that standard normal distribution, such that you have 1 million possible values, z-score slices. Okay? So I would think of it as like, if you got a standard distribution, you have that nice pasta slicer that has the spaces, the even size. It figures out how many, it just slices that distribution into that many pieces, and each of those ranges become what's going on, become the x-axis of your QQ plot. So we did this sort of the manual way. What R allows you to do is there's a function to just do this directly. But before we get into that, what do you conclude about this? If the ideal is, if your data absolutely 100% come from a theoretical distribution, all of your points will be exactly on the line. Part of the art here is deciding from that plot, does it or does it not suggest that your data come from a normal distribution? And there's no right answer here. What do you think? Yes or no? Seeing mostly yeses. I'm seeing some skeptical side eye a little bit, but so in truth, this would be pretty good, a pretty nice QQ plot suggesting that the data come from a Gaussian distribution. But you can also prove it to yourself by comparing your observed data to other distributions. You don't always have to do a norm. You can do this same work with a t distribution or a chi-squared distribution. It's not quite as simple in R, but it's, with about 10 minutes of Googling, you can find the function to compare it to do a QQ plot against a student's t distribution. And then you just basically compare your data versus a normal, your data versus a t in the same plot side by side, and you can get a pretty good estimate of which is better. Yeah.
So with linear regression, you have R squared, and they can calculate p-values with that. Do they do something similar with QQ plots?
Yes, so you can, that's another way of doing it, is you can quantify the correlation between two things with something like R squared. And so the expectation here is that there's a perfect linear relationship between the theoretical quantile and your observed quantile. So therefore, something like Pearson's correlation, which we haven't really talked about yet, maybe a little bit, that's assuming a strictly linear relationship, and you could do it, quantify it that way. Okay, so looks pretty decent for a normal distribution. It's not perfect, and that's partly because of sampling error, right? It turns out, I don't have the time to go into this, but if we collected 1,000 values versus 10. These points that would be closer to that theoretical distribution. And if we did 1,000,000, it would be even better. And that harkens way back to 2 or 3 months ago when we talked about the law of large numbers. The bigger your sample, the better estimate of the population mean and the population standard deviation that you have, and therefore the better your data actually follow the theoretical distribution from which they actually were sampled. Okay, so one thing we don't know doing a QQ plot is a couple things actually. This is non-parametric, so this is just telling us we didn't give R any information about what the mean or standard deviation of our values were, because it's doing everything from that standard normal plot. It doesn't care. It's trying to figure out z-score ranges. The consequence of that is we have no idea what the exact best mean and best standard deviation is that would fit our data. It's just telling us, yes, it is or is not well modeled by a given distribution. And so we don't know, in this case, if it's comparing to a normal, we wouldn't know the mean or the standard deviation. If we were comparing to a t-distribution, we would know the parameters that go into the t-distribution. And the other thing, I think I alluded to this, the other more important thing is there another theoretical distribution that might better model the data that we have? And that's the burden is on us to prove that to ourselves by comparing to other distributions, and as was stated, maybe quantifying that relationship between the theoretical data and the observed data. Okay, so we went through all that work to understand how a QQ plot works, and I think that's important, especially in sort of human genetics. You see QQ plots a lot, and that's mainly used for p-values. You look at a theoretical distribution of p-values versus the distribution of p-values that you have in your data, say from an RNA-seq experiment. This actually isn't done enough in RNA-seq. It really should be done. It's commonly done in GWAS studies, but RNA-seq really should look at the distribution of QQ observed p-values versus the theoretical distribution to convince yourselves that the majority of your p-values aren't inflated. You would expect p-values to be uniformly distributed between 0 and 1, but if most of your p-values are really, really low, that says they're inflated. And you've got a lot of false positives. So that goes into something we'll talk about much later called the Benjamini-Hodgeberg procedure, which is trying to figure out what fraction of your p-values are actually false positives. Okay, digression. But R allows you to compute a QQ plot directly against the normal distribution by just saying QQ norm. QQ plot for the normal distribution, and I can just put in my sorted data, and it generates the same plot. Okay. The key thing is to know how to interpret the plot. Okay, and then we can draw this line, or the QQ line, and it'll do the exact same thing I did with far less Googling and far less difficulty.
So in this case, then you're saying that the line is not exactly diagonal. Is that significant in this case?
We just don't have zero intercept.
Okay.
We just have truncated X ranges. So it's zeros down here somewhere.
I see.
Okay. In other words, it's a y equal x line. Okay. So getting back to our question of whether or not paternal heights are normally distributed, here's the data again. I actually just made a QQ plot. So in this case, let's take some time and actually figure out how many observations there were. You may not have using R already, so you'd have to do the install.packages quote using R thing if you don't. I think we're all familiar with that by now. Okay, so anybody remember the trick to figure out how many values there are from a data frame? How many rows? N rows 1, or you can also just do dim. 1078, or we can do that, and then 2 columns as a sanity check, and also as was stated, n row will give us the same thing. There's 1078. Okay, so there's 1078 paternal heights. So what is our, we're just giving it that data, we're saying QQ norm, we're giving it those 1,078 data points. What's it doing behind the scenes to figure out the theoretical?
Kind of a lot of bits to 1,078 pieces.
1,079, yep. So basically now we've got a much narrower gauge slicer of that distribution, and it's slicing that up so that each end of each range is the z-score associated with 1 over 1,079% of the distribution, right? And that's the z-score cutoff that gets put in on the x-axis, and on the y-axis is the paternal heights. So let me do that as well. Oh, whoops, wrong slide. I've sorted this. I actually wonder, I don't know if you even have to sort it. I think it might be clever enough to just sort it behind the scenes. Yep. So you don't even have to sort it. Okay, so we've got the quantiles go out to 3 point something and minus 3 point something. And each of these, there's 1,078 points on this plot, and each of these points coincide with some very small, precise z-score range from that standard normal distribution that has been sliced up into 1,079 slices that have the same area under curve. And you know what? That looks pretty good, right? What's missing is the line. So let's draw that on there. Yeah, that looks pretty sweet. It's a little ragged out the tails. So our least common values at the low end and high end are a little bit deflated with respect to what the theoretical distribution might predict. And I think that probably comes from the fact that, again, we only have 1,078 values.
And also it could be mother, right?
Right. Well, yeah, and also well, this is just father's heights.
I know, but because the sons could be influenced by the mother's.
Yes,
too.
right.
So that's why when the extremes, the father could marry someone who's like really short.
Right. But we're not plotting son's heights here.
Oh,
We're just looking at father's heights.
Oh, just father's height.
Yeah.
Oh, because that's
But the same goes for that father's parents, I think is your point. So, not surprisingly, this fits a Gaussian distribution pretty darn well because I think it's pretty well known that heights are sort of like a canonical normally distributed trait. So that's somewhat comforting that it actually does look like it's normally distributed. Okay, just to wrap up with a couple more slides here. Let's do a positive control experiment though. Let's make sure, let's simulate data from a normal distribution as our observed data, and then run a QQ plot against that to make sure that our heights data, the QQ plot for our heights data, looks almost as good as a QQ plot from data simulated from a normal distribution. Okay? So in this case, I'm just taking, I forget where I got a mean of 67. Oh, I computed the mean and standard deviation from this data set. So those are the parameters of a normal distribution that I'm creating, and I'm generating R, random numbers from that. So we've talked about D norm, P norm, and R norm. D norm is density, the PDF values, the probability of any particular value. P norm is from the cumulative density function. What is the probability of that value or less? And R is random values, generate random values from a normal distribution with a mean and a standard deviation. So these are all, the R, the P, and the D for normal distribution, Poisson, T, chi-square, they're all available in R, and they're weapons, right? I mean, you know how they all have the same utility. You just change, the parameters are different. For Poisson, it would be just lambda. For normal, you give it a mean and a standard deviation. I can't tell you what the parameters of the other ones are, but we'll learn in good time. But what's nice is the nomenclature is consistent. Okay, so we've got our observed data. Let's actually call that sim. This slide's broken a little bit. Let's just call that simulated data. Right? And so there is the QQ plot of our simulated data from a mean and standard deviation of defining a normal distribution against the theoretical quantiles. And if I go back one plot, that's the Galton data, the QQ plot for the Galton data. And if you look, yeah, the simulated data fits it a little bit better. It's peeling away less at the extremes of the distribution, but they're pretty decent. Let me convince you of that a bit more by doing a negative control. So the positive control was make sure that the QQ plot actually is beautiful along the diagonal when we generate data from a normal distribution, and the theoretical quantiles come from a normal distribution. A negative control would be, well, let's simulate data from a chi-squared distribution and do a QQ plot of that against the normal distribution to see what a crappy QQ plot looks like, right? So again, let me make this simulated for better variable names. So I'm going to simulate 100's kind of lame. Let's do 1,000 values. Chi-squared only has one parameter. I hard-coded it as 3. Better coding would be to define what that parameter actually is. I don't know, but maybe I can fix that now. So let's do it this way. N equals 1,000. That's the number of variables, random chi-squared variables that we're going to generate. And then degrees of freedom is the parameter. Okay. So we got simulated values, lots of them. Okay. Then I'm going to do a QQ plot of that simulated data from a chi-squared distribution against the theoretical quantiles from a normal distribution, right? And it looks mooey worse than this one, right? It's like, it starts peeling away. So here's some basic observations. It starts peeling away from the theoretical quantiles at 1 z-score away from the mean. That's ugly. That means the tails are really, really off. Okay, so another way of saying this is the normal distribution would model this data, would model about 66% of the data well in sort of the center of the distribution, but it would be, all bets are off beyond 1 standard deviation. Okay, that's all I have. Does that make sense? We have a couple minutes. The QQ plot stuff gets a bit abstract, I think, but if you have questions, feel free to ask me. If you have them now, I'm happy to answer them. Otherwise, we can converse over Slack. Just quickly looking forward, if any of that was difficult, this write-up from a former colleague of mine at UVA is really wonderful about how QQ plots work, some of the theory, and some really nice examples that go into a little more depth than what I had time for. And then hopefully on September 30th, I'm thinking I can fit that in. We're going to talk about the central limit theorem, which is sort of fundamental to statistics, especially the t-test. If you use t-tests, you need to understand the central limit theorem. And we're going to talk about confidence intervals, how they should be used and how they should not be used. That'll set us up to talk about the t-test in the following lecture. Then after that, we're going to talk about what p-values are and what they are not. And then we'll transition into regression. If you could, before September 30th, this 2 to 2.5 page article called The Importance of Being Uncertain. It kind of sets up the motivation for t-tests and primarily the central limit theorem. Yeah? Yeah, I've been recording them all. Yep. Any other questions? All right, thanks so much.